So this is a practice video on geometric vectors. And what I want you to do is to follow along with some drawings. So make sure you've got a ruler and a pencil and a piece of paper. So first of all, we're going to draw a line going along here. And we're going to draw a line going from a third of the way along here down perpendicularly like this. Then we're going to join this up. And if we measure along this diagonal line to here, we should find a midpoint right there that we can then join to this end point up here. Okay, so that's completed our drawing, and if you haven't done it so far, I urge you to pause the video and just copy the drawing. Okay, now what you should find is that this line here has been divided in a 2:3 ratio. In other words, this is 2/5, and right here this is 3/5. So if we now label this diagram, we can overlay some vectors onto it so that this will be A and 2B, and this will be A and 2A, and this will be 2B and 3B. Okay, so let's have a look at that now. Okay, so that's completed the diagram. Now what we're going to do is give ourselves a theorem. So the theorem will look like this. So show that M, L and D are collinear. So M, L and D are on the same line. Okay, again, time to pause the video and see if you can prove that theorem. Okay, so the very first thing in any proof is to write very clearly what it is that you want to prove. And in this case, what you should have started with really is this. So we write down exactly what we want to prove. What do we want to prove? We want to prove that M to L, M to L, let's just neaten that up a little bit. Okay, so M to L is parallel. M to L here, so mark that on like that, is going to be parallel to L to D. L to D. That's the key insight that you need. You'll also need just to say the visually very obvious but important point that ML, vector ML and LD share a common point. I'll just put share L. Okay, you could express that as M to D equals M to L plus L to D. It's not quite the same thing. I think the main thing is just to say that they share a common point. So prove M to L anyway is parallel to L to D. That's the key insight. And again, pause the video at this stage if you like and see if you can do it. Okay, well, how do we prove that M to L is parallel to L to D? Well, first of all, we need to work on M to L, and we don't know what M to L is, so we need to think about other ways of getting from M to L. So if we go around from M to A and then up from A to L, that should do it. Again, if you want to pause the video at this stage and see if you could do that little stage, see if you can get from M to L via M to A and A to L. Okay, so from M to A is, there's no vector where we can easily do that, but what we do know is B to A. So I'm going to start with B to A, which I know b to a I can get to via this route here, b to n. So b to n plus n to a. Okay, so now I can write b to a, and again pause the video and give it a go. Okay, so b to a can be expressed as, then, if I write it underneath, b to n is a, and n to a, well, that's going to be negative 2b minus 3b. So these are going in the opposite direction, so these are negative. So it's going to be minus 5b. Okay, so now I've got an expression b to a. I should be able to write down an expression for m to a. Okay, so m to a, write it here actually, it's going to give us a bit more room. Therefore m to a is half of this expression here, so it's going to be half of a minus 5b. And if we expand our brackets, then I've got half a minus 5/2 b. So that's given us an expression for m to a. Now let's work on m to l. So again, if you want to pause the video here and try this yourself, you should be able to get an expression for m to l now. So m to l is m to a so let's draw that on our diagram, m to a. Whoops, that's a bit untidy, let's tidy that up. Okay, so that's m to a plus a to l. So we now write that down in terms of a and b vectors. So m to a is half a minus 5/2 b plus 3b. A to l is 3b. Okay. And if I look at this, I've got minus 5/2 b, so that's 5/2, in other words 2.5. So negative 2.5 plus 3b, so I'm going to end up with half a plus half b. Okay, now I need an expression for L to D. So again, opportunity to pause the video if you think you've got the hang of it now and complete L to D. So L to D needs to go along here from L to N and from N to D. So it's from L to N plus N, there we go, to D. And if we write that in terms of the vectors, we've already got those vectors, so it's 2. So N to D, I can commute vectors, of course, so I'd start with N to D because then my A is going to come up front. 2A plus my L to N, which is 2B. Okay, so now how do I prove that M to L is parallel to L to D? See if you can pause the video and give that a go. Well, okay. The technique that we usually use is we know that if M to L is parallel to L to D, then it's going to be M to L is equal to some constant K times L to D. So I'm going to say let K equal, well, what do I want here? Let K equal a quarter. Okay, so looking at my figures, I can see that a quarter is going to work. So as long as there's some constant K that will multiply L to D to give me M to L, then I'm going to have proved that, that M to L is parallel to L to D. Okay, so let's give that a go then. So if I say, okay, so L to D, so quarter L to D equals a quarter of this expression here, 2a plus 2b, then that equals a quarter times 2 is half a, and a quarter times 2b is half b. Okay, let's just tidy that up a little. There we go. So, therefore, I've proved that ML must be parallel to LD, and we can just put as required, which is what we needed to show. So that completes the proof for part 1, and now we can move on to part 2. So this time let's draw a triangle like this. Not necessarily an isosceles triangle, but a nice simple way to draw it. And what I'm going to do is measure the midpoints of these two sides here, so two adjacent sides, and if I draw those together, then I end up with a line which looks suspiciously parallel to this line here. Well, of course it is. And what we're going to do now is just prove the fairly obvious. So a simple proof here, and if you've followed the proof that we gave here so far, if you feel confident now, this is a very nice one to try and develop your own confidence. Pause the video and give it a go. So before you do that, let's just say what the theorem is. So if we label all our parts here, in fact what I'm going to do is put some values on here. So if I join these together like this, and yes, what we'll do is we'll put these on here like this. Okay, so that we've got a vector A going from A to P, and from Q to B, just to spice it up a little bit, I've given this a value 4b, so it's 4 times a smaller vector b. Okay, so what we've got to show, first of all, is that P and Q are midpoints. If P and Q are midpoints, then we need to show that PQ is parallel to AB. So if you're confident, pause the video and give that a go. Okay, so the first thing you should always do with a proof is spell out exactly what it is you want to prove, and in this case what we're doing is we're trying to prove that PQ, but this time in terms of vectors, so P2Q, let's say, P2Q, we could have gone in the other direction, but that's seems the most natural way of doing it. P to Q is parallel to A to B. So that's the first stage, define your proof. Okay, so next stage I'm going to start with, let's start with A to B. You could start with P to Q, but well, okay, let's start with P to Q. Maybe that makes more sense. So let's start with P to Q, but if you want to start with A to B, that would be fine too. Maybe give it a go both ways and see how it works out. Let's start though with P to Q. So let's write down here P to Q, and again pause the video if you're ready to do this for yourself. So P to Q can be obtained by going from P to C. That's the resultant vector of P to C added to C to Q. Okay, so P to C will be here, and because P is a midpoint, we know the vector PC is going to be A, so it's equal to the vector AP. And if we go from C to Q, well, we've got 4B, because C to Q is equal to Q to B. So 4B, not 4C, 4B. Okay, like that. So now you need to express PQ equals P to C plus C to Q in A and B terms, in terms of A and B. Pause the video, give it a go. Okay, so P to C is A, and C to Q is 4B. And that's halfway through our proof. So now we're going to work out A to B. So again, if you're confident, pause the video, write down an expression for A to B, and then in terms of A and B vectors, and see if you get the same result as I do. Okay, so A to B, we're going to go in this direction here, so along there. But to get there, we're going to go from A to P, and then we're going to go from P to C, then down from C to Q, and down still from Q to B. And all the vectors very nicely pointing in the right direction, so very easy. Okay, so again, pause the video and write down this this expression in terms of A and B vectors. Okay, so A to P is A, P to C is also A, C to Q is 4B, and Q to B is also 4B. And now gathering the terms up, A plus A is 2A, 4B plus 4B is 8B. And that completes our writing P to Q and A to B in terms of A and B vectors. The next and final stage is to prove that P to Q is parallel to A to B. So pause the video if you know how to do that and give it a go. Okay, well, to prove that P to Q is parallel to A to B, we know that that would mean P to Q is equal to some constant k times A to B, scaling A to B. So what would that constant k be? Well, we can see that A to B is twice P to Q. You can see 2A and A, 8B and 4B. So all we need to do is say let k, let our constant k equal a half. So p to q, that's not a very clear equal sign, let me just neaten that up. K equals half. So p to q is going to be half, if this works, p to q is going to be half a to b. Well, a to b is 2a plus 8b. And that equals half times 2 is 1, so just a, plus half times 8 is 4, so 4b. So we've shown that, therefore, p to q, I can say equals some constant k times a to b. Therefore, p to q must be parallel to a to b as required. And that completes the proof. Finally, let's draw a parallelogram. So something like this. Across here, down here, join that across. So there's a parallelogram. So we're going to define this now as a parallelogram. And if I join the diagonals up here, a bit like we did here, we didn't actually need these diagonals. This would be the diagonals of an isosceles trapezium. And you might want to think of a theorem that talks about the midpoint here. I'm going to talk about the midpoint of a parallelogram. Well, let's just label this up then. So if V is the midpoint and RSTU defines the parallelogram, then I've drawn on here vector A must equal this vector here. So in other words, R to V is the same as V to T. So vector A is defining this midpoint here. Now, the theorem is that we're going to prove if V is the midpoint of RT, then V must also be the midpoint of ST. So show that V is the midpoint of SU. Okay, show that V is the midpoint of SU. So pause the video and give that a go. Okay, so what have we got to prove exactly? Well, the first thing is to define exactly what we're going to prove. We're going to prove that a vector drawn from here to here must be equal to a vector drawn from here to here. In other words, SV, vector SV, is going to be exactly equal to the vector VU. Okay, and if you're confident that you can do that, pause the video and give it a go. So what we need to do first of all is define another vector. So to get from S to V, we need to go down here and up here. So it makes sense to draw our vector in this direction, so that now we have S to V equal to S to R, S to R plus R to U. So express S to V equals S to R plus R to U in terms of A and B. So now we've got an expression for S to V. The next thing we need to do is fill in our A's and B's. Okay, so there we go. S to R is B and R to U is A. But I'm going to commute them because I just want them in order. Quite easily do R to A plus S to R. So in other words, r to a, r to, what are we doing? R to u. We wanted r to v, didn't we? Whoops. So let's just erase that. Oh, there was something wrong. No problem. So r to v, and then we'll fill it in again. So r to v is a, so just commuting as I'm going along, and s to r is b. Okay, now next bit of the proof relies on the fact that RSTU is a parallelogram. So if you're happy with that, pause the video and give that a go. Okay, so you should have realized that if this is a parallelogram, then we can define an equal vector on the other side of the parallelogram, t to u, which we can also label b. So therefore, v to u must equal v to t plus t to u, which if you express in terms of a and b vectors, v to t is a and t to u is b. Therefore, s to v is equal to v to u, which means that SV equals VU, which was what we needed to show, so as required. Okay. This last problem actually is quite interesting to think in a slightly different way. So what if we defined here now this vector here C and work our way around this in a slightly different way. So if I'm trying to get S to V, how about thinking about it in terms of now vector C? So vector C is from S to T, so let's just define this as S to T. So S to T, well, we could go down from S to R and along from R to T. So this alternative way of thinking about the problem will give us B plus 2A, or 2A plus B. If that's the case, if we now have C equals B plus 2A, when we start thinking about S to V, we'd have just a slightly more complicated expression. S to V would be the same as S to T plus T to V. And now perhaps you'd like to just pause the video and fill that one in. So S to T, well, we've got S to T here, that's B plus 2A, so I'm going to just commute it, 2A plus B. And T to V, well, that's the reverse of V to T, and V to T is A, so it must be minus A. That gives us 2A minus A plus B. And you can think about doing the same thing with V to U. Okay, so V to U would be, if we wanted to use that C, the R to U direction, we would go again minus A. Now I've got R to U would be C, so it'd be plus 2A plus B. Again, giving us minus a plus 2a, in other words a plus b. Therefore, using a slightly different way of proving it, we've proved that s to v must equal v to u as required. And that completes the proof.